Alright, ladies and gentlemen, this video serves as our introduction to section 5.3. The name of the section is limits involving infinity, but what this section is really about is horizontal and vertical asymptotes. The graph that we're going to use here at first to explore horizontal and vertical asymptotes is the graph y equals 1 over x. This is a good one to use because we can see this graph has both horizontal asymptotes, or at least a single horizontal asymptote and a single vertical asymptote. So we're going to take a look at how we can calculate precisely where these magical lines exist. Just to give you a little explanation of what's going on in the screen, I have a general equation over here with many variables, a, b, m, and n. For now, m and n are both set to 0, and a is also set to 0. So on top we have a to the 0, which is just 1. That's where the numerator comes from. And on the bottom we have x to the 1 plus 0. That's where we have this. So we just have a general form. We're going to play around with these sliders a little bit to see how we can manipulate these asymptotes. But for now, we're just going to stick with the basic function 1 over x. Let's start by looking at vertical asymptotes. So vertical asymptotes you might be actually more familiar with. It's something that's covered in algebra and pre-calculus a little bit. Vertical asymptotes occur when division by 0 occurs. And clearly in y equals 1 over x, that's going to occur when x equals 0. Now, you can include this idea in a section on limits if you consider it this way instead. Just take a look at the bottom of the function, the denominator, which is just x. Well, we can think of this as a limit. The limit as x approaches 0 from the right of the denominator is 0. This is basically saying the same thing as setting it equal to 0. Technically, it's just a little bit different. You get the same result when you approach x from the left as well, of x equals 0. This is just a way to kind of thoroughly demonstrate that there is a vertical asymptote on this graph. If we consider a function, a similar function like y equals 1 over x squared minus 1, for instance. So what we're looking for are x values that cause division by 0. And, you're probably okay with just solving an equation that sets the denominator equal to 0. If we do this, we get x equals plus or minus 1, which suggests that there's going to be two vertical asymptotes for this graph, one at x equals 1 and one at x equals negative 1. It's saying the same thing, but using the language of limits, we'd say that as x approaches 1 from the right, x squared minus 1 becomes 0. And that's the denominator right there. X squared minus 1 is the denominator. So using limits, we can say that the denominator will approach 0 as x approaches 1 from the right or the left. And the same thing with negative 1. We can confirm this with a graph. We can take a look at the graph y equals 1 over x squared minus 1. Let's just go, we can manipulate our sliders in this formula. Let's see here, we'll keep a at 0, and this time we'll change the exponent at the bottom to 2, and we'll change n to negative 1. And sure enough, we can see that we end up with a function with two vertical asymptotes, one right here at negative 1, and one right here at positive 1, just as advertised. It also appears that we still have a horizontal asymptote at 0, so that didn't change, interestingly enough. If we consider the equation 1 over x squared plus 1 instead, so I've changed the values of n from negative 1 to positive 1, we can see there no longer are any vertical asymptotes. Well, that's because if we try to do x squared plus 1, if we try to get that equal to 0, it's not going to work because there are no values of x such that x squared is equal to -1. So there are no vertical asymptotes. You can only get vertical asymptotes when the denominator can equal 0. So now let's take a look at horizontal asymptotes. Horizontal asymptotes occur when you get a number answer for a limit that approaches infinity, either positive infinity or negative infinity. In other words, if we take a look at the function 1 over x and describe what happens to the graph as x approaches infinity, we actually approach a number with the number 0. When this occurs, we have a horizontal asymptote. It just so happens that as we look at how this graph behaves as x approaches negative infinity, we also get 0. But this doesn't necessarily have to occur. Only one of these limits has to equal 0 for a horizontal asymptote to exist. All this means is we get the same behavior on the far left part of the graph as we do on the far right of the graph. So let's go back to our sliders and just kind of play around with this general formula for a little bit. I'm going to set m and n back to 0. Let's just go back to 1 over x. Now, if I raise the exponent of the denominator, so right now we have 1 over x to the first, and it looks as though we have horizontal asymptote at x equals 0. Well, if the exponent on the numerator continues to increase, it doesn't change the fact that we have a horizontal asymptote at 0. But what happens if we have an exponent on top that's greater than the exponent on the bottom? So this, for instance, would represent x to the fourth over x to the first. In fact, we can do something like this. So here's a function here. This represents x to the fourth plus 1 over x to the first plus 1. So there's a couple of ways to think about this. If we remember what that graph looked like, it was pretty clear that there was not a horizontal asymptote. And we can show this algebraically by doing a little trick. Okay, here's what I'm going to do. I'm going to take this entire fraction and I'm going to multiply it by 1 over x to the fourth. And the reason I do this, well, I guess you'll see why I do this in a second. This is a useful strategy to kind of explain things, but once you see the pattern, you won't really need to do this anymore. So let me just show you what happens. We distribute 1 times 1 x to the fourth times 1 over x to the fourth is, I'll just write it all out. Let's just write it all out. X to the fourth over x to the fourth plus 1 over x to the fourth all over x to the fourth plus 1 over x to the fourth. So all I've done is I've divided everything by x to the fourth. And I end up with x to the fourth over x to the fourth is just 1. So I get 1 plus 1 over x to the fourth plus 1 over x to the third plus 1 over x to the fourth. Now it may seem like this isn't doing us any good. It's just making it more complicated looking. But what we can do, we already know that the limit as x approaches infinity of 1 over x is 0. If we start with this premise, then we can take a big ugly looking thing like this and just kind of break it into its pieces. The limit as x approaches infinity of this big monster, well, the 1 is untouched right now, so because this doesn't have x in it at all. So as x approaches infinity, the 1 is not affected. This guy, though, is affected. As x approaches infinity, 1 over x to the fourth is going to approach 0. So the limit as x approaches infinity of 1 over x to the fourth over 1 over x to the third plus 1 over x to the fourth. What we're going to find is that we are not going to get a number answer for this. We are going to get a limit that does not exist. We get 1 plus 0 over 0 plus 0, which does not exist. Since we have a limit that does not exist, That means there is no horizontal asymptote. The trick, though, if you just need a quick answer, the trick is you look at the highest exponents in the numerator and in the denominator. The highest exponent in the numerator is a 4. The highest exponent in the denominator is a 1. Well, as x gets larger and larger and larger, you could think of it as like a battle that's occurring. X to the fourth is going to outpace x to the first. Eventually, the graph just kind of goes off into infinity, and there is no horizontal asymptote. Another example might be y equals x to the third plus 1 over x squared plus, I don't know, 1, whatever number that is. Now you may think, oh, what is that, 1 million? That 1 million on the bottom is really going to change things. Well, it's true. At the beginning, if we just take a look at like f of 1, well, 1 plus 1, we're going to get 2 over 1 million and 1. So yes, it's true. At the beginning, the numerator is going to be bigger than the denominator. But inevitably, as the numbers get bigger and bigger and bigger, when we do f of 1,000, for instance, this 1 million just isn't going to matter anymore, because the x to the third is going to get significantly larger and larger and larger compared to the x squared. So f of 1,000, 1,000 squared plus 1, or this should be 1,000 to the third power plus 1, is going to be more significant. I think I'd have to check the numbers, but I think it's already going to pass that. I'm not exactly sure, but you can see that given time, the numerator will in fact pass the denominator. Let's look at one last example. This is number 10 on page 275. It asks for the limit as x approaches infinity. I just look at the largest numerator on top, which is 5. I look at the largest numerator on the bottom, which is 2. The rest I can ignore completely. I know that the numerator will win out in the end, and we will have no horizontal asymptote. This limit does not exist. You could sort of get away with saying that the limit equals infinity, but that's not really technically right. We would say that the limit does not exist. You can say that the graph sort of tends towards infinity, and people will know what you're talking about. So to summarize, when the exponent on top is larger, there is no horizontal asymptote. The graph seems to just go off to infinity. When the exponent on the bottom is larger, we get a horizontal asymptote of 0. So that leaves us with the one other scenario, which is if the exponents are in fact the same. So let's take a look at this. Let's just give some arbitrary values for m and n. So this is the function x to the third plus 2 over x to the third plus 1. And it looks as though we have a horizontal asymptote, and we need to figure out where that is. While we're at it, we'll also take a look at where the vertical asymptote is. So let's actually start with the vertical asymptote. The vertical asymptote is going to occur when the denominator equals 0. And this happens at the cubed root of -1, which is just -1. So x equals -1 is a vertical line. That vertical line represents the vertical asymptote of the function. For the horizontal asymptote, I'm going to show you a long way to do it and a short way. The long way to do this is to divide everything in the function by x to the third. So we have x to the third plus 2 over x to the third plus 1. And we're going to divide all these guys by x to the third because we can. Why x to the third? I chose the largest exponent available. And I'm going to divide everything by that. And what I end up with is f of x equals 1 plus 2 over x to the third over 1 plus 1 over x to the third. The reason I do this is because I'm taking advantage of the fact that I know this limit. I know that as x approaches infinity, 1 over x becomes 0. I know this, and so I'm doing this little trick by dividing everything by x to the third to take advantage of this. If this is true, that means this and this are both going to go to 0 if I take a look at this limit. The numerator becomes 1 plus 0. The denominator becomes 1 plus 0. So I do get a number answer. The limit as x approaches infinity gives me a result of a number. When this happens, that means I do have a horizontal asymptote, and this is at the line y equals 1. Sure enough, this corresponds to what we saw in the graph. A vertical asymptote at -1 and a horizontal asymptote at +1. The shortcut for this problem, if you don't like this idea of dividing everything by x to the third, there's a nice little shortcut that you can use. And the shortcut is, you take a look at the terms in the numerator and in the denominator. And if you have matching exponents, which we do here, you take a look at the largest ones and you look at their coefficients. So the coefficients of this are 1 over x to the third plus 2 and 1x to the third plus 1. So the coefficients will give you the horizontal asymptote. We end up with just 1 over 1. This is going to be true in any sort of problem. So let me give you another one. How about, I don't know, y equals, we'll do one from the book. It's a limit problem from the book. This is number 8. I look at the numerator, I look at the denominator, and I look at the largest powers. So if this number was bigger than this number, then there would be no horizontal asymptote. This graph would tend towards infinity. If the numerator denominator, if this 2x squared, if this 2 was actually larger than this exponent here, then the horizontal asymptote would be at 0. The graph would tend towards 0. Since they're the same, I look at the coefficients, 3 and 2. The limit of this function is 3/2. What that means is that y equals 3/2 is a horizontal asymptote of the graph. We can confirm this using our little trick that we used earlier. We divide everything by x squared, then clean it up a little bit. So we get, when it's written like this guy and this guy and this guy are all going to tend to 0 as x gets larger and larger and larger. All we're left with is the 3, that was the original coefficient up top, and the 2, so the limit is 3 over 2. So that's all for now. I think you have enough background to do any problem from this section. I'll assign a couple, and there it is. Have a good day.